So last time we started talking about Fourier series, and what we saw was that the Fourier series for a function f of x is given by some a naught over 2 plus a sum n equals 1 to infinity of, and then we had cosines plus sines. And these constants were given by, an integral, and the integral was 1 over pi minus pi to pi, and then we had inside f of x, in this case cosine of nx dx, and for bn we had 1 over pi integral minus pi to pi, f of x sine of nx dx. Okay, and so this is what we introduced last time, but now what I want to do is start actually doing some examples with this, actually performing some calculations. And so the first example that I want to do is with a square wave. And so a square wave is something like this. We have 1 if x is greater than 0, and minus 1 if x is less than 0. And graphically, this looks something like this. We'd have plus 1 up here, up until we get to pi, minus 1 down here until we get to minus pi, and then Fourier series is periodic, and so it continues. So we have something that looks kind of like that. And square waves are really important in signal processing and electronics and a whole bunch of places. And so let's go through and calculate this. Well, how are we going to do it? Well, we got to get these ANs and BNs. And once we have those, we have our series. So let's look at this and think what we're going to get from it. Well, what do we know? We know that this f of x right here is an odd function, right? Okay. Well, what does that mean for these ANs here? Can we have an odd function that's built up out of cosines, which are even functions? Well, no. And we can see that right from this integral definition, right? We're going to be integrating an odd function times an even function, both centered at the same point, over some even interval. And so because of that, we can immediately, without doing any math, just see from the symmetry of everything here that these ANs are equal to 0, all of them. And this is one thing that's going to come up a lot when we calculate Fourier series, is that in most of the examples that you're going to do, right from the get-go, there's going to be some symmetry, either the function's even or odd, such that half of these terms drop out. All right, so in this case, this function's odd, so all of these even terms have to drop out. Boom. All right, great. What about these BNs now? Now, well, this function's odd, these signs are all odd, and so, we're actually going to get some contribution here, so we actually have to do some integration now. And so, how is this going to work? Well, this is a piecewise function, so usually the thing to do here is to split up the integral into two parts. And so if I do that, what are we going to get? We're going to get 1 over pi out in front of everybody. Then we'll have an integral from minus pi up to 0. And there we'll have a minus 1, so we'll have minus sine of nx dx plus, and then the other part of the integral is integral 0 to pi. Here we're going to have positive 1 sine of nx dx. Okay, great. So these are easy integrals to do. What happens? Well, let's take a quick look at this first piece right here. One thing we might notice is that if we use a change of variables, x going to minus x, what's going to happen? Well, our signs in the bounds of integration are going to change, so this is going to become a pi to 0. We're going to get a minus x right here, and so that's going to pull out another minus sign, so this becomes plus. Then we have a minus x right here, which we can use to swap these bounds of integration. And so this whole thing actually is equal to just 2 times this one integral, 0 to pi sine of nx dx. All right, so we only have to do one integral instead of 2, and that's nice. And it's an easy integral. We know that integral of sine is minus cosine, so we're going to get minus 2 over pi cosine of nx over n, evaluated from 0 to pi. Okay? Now we have to stop and think a little bit. So this whole thing right here is minus 2 over pi n, and then the hard part, cosine of n pi minus 1. So let's think about what this is going to be for different values of n. Well, for n equals 1, we're going to have cosine of pi. Cosine of pi is minus 1. So for n equals 1, we're going to get minus 4 over pi times, well, in that case, n equals 1. So 1. Okay. What about n equals 2? Well, for n equals 2, this cosine of 2 pi is going to be equal to 1. And so this is going to be equal to 0. 1 minus 1. And then you can see, well, then for n equals 3, we're going to get back another minus 1. So this is going to be minus 2 times a minus 2 out in front. For n equals 4, we're going to get back to 0. And so what these terms are equal to are going to be 4 over n pi for n odd and 0 for n even. So these are our coefficients. And let's make sure this is clear, right? So this cosine n pi is going to determine whether or not this thing's equal to 0 or something. And for even n, cosine of even n times pi is equal to 1, so this thing goes to 0. Odd, you get a minus 1, and then this adds up. So this makes sense. But so we've done it then. We have our coefficients figured out right here. And so we can say that our function f of x is equal to, it's going to be a sum over n odd, and it's going to be 4 over n pi times sine of nx. All right, so we've done it. We've done it. And a good thing to always do whenever you do any Fourier series problem like this is to actually plot your function and make sure your results make sense. So I've already done that on the next page, and so if we look at that, let's see. So when we plot our function, and here, so what am I plotting here? I'm plotting partial sums of the Fourier series. So here I'm plotting all the terms. Here I'm just plotting the first term. Here I'm plotting all of the terms up to n equals 9, then all of the terms up until n equals 79. And so what do we see? We see that for n equals 1, we have just a sine wave. Okay, that's sort of the lowest type of approximation we can get to a square wave. So that kind of makes sense. And then for n equals 9, what happens? For n equals 9, we start getting something a little bit more accurate. You can see it shoots up a lot faster, and then it kind of hangs out up there, and then shoots down, hangs out down there, and shoots back up. So getting better. And then for n equals 79, so a much more accurate approximation, we see that it shoots up a lot, then it settles down real nicely to about a constant 1, shoots up, then back down to a constant minus 1. And so we can see then that, all right, the results we're getting are making sense. So our Fourier series in the previous case was correct. So that's good. So, okay, great. Let's do another example. And the example I want to do now is for the function absolute value of x. F of x equal to absolute value of x. And so graphically what this should look like is something kind of like absolute value, but periodic. And some people call this a triangle wave. So let's actually do this. Well, and first let's think about our coefficients again, right? So we know that the a-n's, or the cosine terms, correspond to the even terms, and this is an even function. And our sine terms, or our bn terms, correspond to odd terms. But kind of like the previous case, this is just an even function. And because of that, we know if we integrate an even function multiplied by an odd function, you're going to get 0. So all of our sine terms drop out. And so the only thing that we have to calculate in this case are our a-n's. And here our a-n's are equal to 1 over pi, integral minus pi to pi, absolute value x d, or absolute value x times cosine of nx times dx. And I'm going to do something a little different in this case. So you'll recall, and I'll pull up the first page. In our Fourier series, with our a-n's, we have two things going on. We have an a0 out in front, and then we have a sum for all the other a-n's over here. And oftentimes it's easier just to calculate a0 from the get-go and then do it in general for an, because it's not always easy to look at the case when n equals 0. So that's what I'm going to do. I'm going to first calculate a0. So what's a0 going to be in this case? Well, it's going to be cosine of 0 is 1, so we're just going to be integrating 1 over pi, integral minus pi to pi, absolute value of x. All right, well, this is one of those instances where, you want to split up the integral. So what are we going to get? We're going to get 1 over pi minus pi to 0, and here it's going to be minus x. So x is always minus on this domain, then we have minus x. So that's good. Plus 0 to pi x dx. Okay, now what? Well, same type of trick as before. Because this is an even function, we can use the change variables x to minus x here, and what happens? We get plus x here, minus sign here, minus sign here. We can flip it all around, and we simplify this integral to just 2 over pi integral 0 to pi x dx. And this is an easy integral to do, and what we get is pi. Okay, great. So we know then that a0 in this case was equal to just pi. Okay, good enough. What about an? Now let's do it for the more general case. Well, for the more general case, I'm going to, for the more general case, it's going to be the same type of story. And so I'll skip ahead a little bit, anticipating that, we're going to split up the integral, but because it's an even function, it's going to cleanly just end up being 2 times the integral of the right-hand side, because it's even. That makes sense. So the only integral that we have to do is integral 0 to pi x cosine of nx dx. All right, so as soon as we do this integral, we are set. We've got it. All right, so how do we do it? Well, here the trick is to use integration by parts. And if we use integration by parts on this guy, what are we going to get? Well, what we're going to want to take a derivative of this guy, integrate that guy. So what are we going to get? We're going to get x over n times sine of nx. So here we've left this term alone, integrate the cosine, and we're evaluating this guy from 0 to pi. Okay, then minus integral 0 to pi. Well, derivative on this guy, integrate on this guy. So we're just going to have sine of nx over n dx. Okay, so first let's look at this term right here out in front. What we'll notice is that we have sine of n pi over n minus 0. 0 times sine of 0. So what this means is that for n greater than or equal to 1, which is what we're considering, we already did a equals 0, this whole thing right here is going to be equal to 0. Right, because sine of n pi is equal to 0 everywhere, and we don't have to worry about some n equals 0 over n equals 0. So this whole thing's just going to be equal to 0. Okay, what about this last piece over here? Well, what happens? We have 2 over pi integral 0 to pi sine of nx over n dx minus sine out in front. All right, another easy integral to do, right? We know that if you integrate sine, what do you get? You get minus cosine. So this whole thing's going to be equal to 2 over pi n cosine of nx evaluated from 0 to pi. Right, and so this is going to be 2 over n pi. Well, and actually what happened, well, I've cheated a little bit. We're pulling out a second n when we do this integral. So we have 2 over pi n squared cosine nx evaluated 0 to pi. What do we get? We get 2 over n squared pi times cosine of n pi minus 1. Okay, and this is exactly what we had in the previous case. Here for even n, this is going to be equal to 0, and for odd n, we're going to get a minus 2 right here. And so these terms are going to be equal to minus 4 over n squared pi for odd n, and then 0 for even n. All right, and so we've just about got it. Now we just have to write down our full series. So our Fourier series for absolute value of x is going to be, well, what's it going to be? It's going to be a naught over 2. So that's going to be pi over 2 plus, then we're going to have a sum from, or over odd n, And what's it going to be? It's going to be minus 4 over n squared pi cosine of nx. Okay, so we've got it. Now, just like in the previous case, we always want to make sure that our answer makes sense. And we do that by plotting it and making sure, does this thing actually look like what we expect? And so I've already done that again. And so when we look at that, this is what we see. So these are our triangle waves. And here I'm doing the same thing. I'm plotting terms up until n equals 1, n equals 9, and n equals 79. And so what do we see? Well, we see that for n equal 1, this blue curve right here, it's just a cosine, and that's sort of, naturally the first approximation we could do with Fourier series is just say, all right, well, let's just call this thing a cosine. So that's easy. But then you see this n equal 9 and n equal 79 curves. I mean, it's actually really hard to see on this plot because, the two are almost exactly on top of each other. We see in this case, just going out to the n equal 9th term, you get a very, very good approximation to your triangle wave here. And so we see that, all right, this is actually, our Fourier series does make sense. When we plot it, we really do get a triangle wave that looks great and confirms with our intuitions.